pleasure to introduce this week's colloquium speaker, Karsten from Notre Dame University, and he's going to tell us about positive recurve manifolds. I'm very excited about this talk because I worked on the other side of the curvature, namely negative recurve of non-positive recurve manifolds. If you happen to be on the second floor and over here topologists talking, you hear words like hyperbolic, negative recurve, non-positive recurve, cat zero, all the time. So the word positive recurve manifold is very mysterious to me, and I'm very curious about it. And it's very exciting that we have this talk because this is like going to a co-ed college after you've been to an all-girls college. With that, I'd like to present our speaker, and he's going to talk about symmetry and positive curvature.
Thank you. That's a nice introduction. And I'd like to thank Pedro also for inviting me to come and speak here. It's my pleasure to be here again. Well, positive.
One other thing, you got kind of the dean. You're the dean speaker. Did you know that?
Oh, I'm sorry.
You didn't know that. The dean's not here, so you're wrong.
Indeed, positive curvature is one of my personal favorite topics, and it's my pleasure to talk about it here. It, of course, goes back to the beginning of Riemannian geometry and much further, because it's really an extension of spherical geometry. It is true that in the beginning of Riemannian geometry, or global Riemannian geometry, most investigations actually dealt with, first of all, starting with space forms, so positive constant curvature, flat spaces, hyperbolic geometry when it came along. And variable curvature was very hard, and there were no tools really to study spaces or manifolds with curvature changing sign. This certainly changed in the 60s, I would say, and there's a lot of work done now on completely general manifolds or classes of manifolds. But yet, positive recurve manifolds do play sort of a special role in many instances. And I would even argue, I'd like to use this as a motivation also, that today they play a role in the study of all manifolds. In the following sense, if you want to study classes of Riemannian manifolds, for example, those that have a lower curvature bound, this very naturally leads to study convergence of such manifolds, Gromov-Hausdorff convergence. You study more singular metric spaces that have a lower curvature bound. So, and those spaces have very nice structure, and it's very important to understand those more general spaces to understand even Riemannian geometry. Now, what's special about those spaces is that their infinitesimal structure is governed exactly by positive recurve spaces. Okay? So just like if you think about a Riemannian manifold, at every point you have a tangent space. It's a flat Euclidean space. In these more general spaces, every point also has a tangent space, but it's not a linear space. It's a cone on a space. It's a Euclidean cone on a space, and the space is like the unit sphere. It's a unit sphere in a manifold, but in these more general spaces, it's any positive recurve space. Okay? Space with curvature at least one. So positive recurve spaces, in a certain sense, are exactly the spaces of directions, the unit spheres in these more general spaces. So they're important to understand. Okay? And you get feedback from that understanding to classes of manifolds in general. So that's an additional motivation to try to understand that. I'll focus on manifolds, not these more general spaces. And certainly, having, I can't talk about the topic without drawing the unit sphere. So the unit sphere, this has radius 1, is an example of a manifold with sectional curvature constant equal to 1. And I'll only talk about so-called sectional curvature. So this is the unit sphere. And this is in any dimension. And ways in which this is a unique example has given rise to various sort of methods of trying to understand these spaces. Okay? So, so what does it mean that space is positively curved? Well, it actually means that in comparison to the sphere, if you think about two tangent vectors on the sphere, and you follow the geodesic, unique geodesic in these directions, then a space is curved at least as much as a unit sphere if corresponding distances here is less than or equal to what they are in the sphere. Okay? So that's exactly what curves of greater than or equal to 1 means. It means this geometric picture. So you look at an angle, and you go out some distance here, another distance here, and you look at the distance between the endpoints of that so-called hinge. If that distance d, r, compared to d, this has to be less than or equal to d. That's what it means. Okay? So in a certain sense, in comparison to this map on the sphere, this has distances small. Right? So that's the geometric content of having sectional curvature at least 1. Now there are other classical examples. So in addition, so I'll start with the unit sphere, Sn. Then a projective geometry, this is also ancient. Of course, you have the real projective space, but I'm getting that for a moment. So we have the complex projective space, the semiotic projective space, and then the exceptional Cayley plane. These spaces, so this is a space of complex lines in complex n+1 space, quaternionic lines, quaternionic n+1 space. These nets have metrics also with sectional curvature greater than or equal to 1. And if you normalize the metric that way, they actually have curvature between 1 and 4. Okay. These are exactly the rank 1 symmetric spaces. The simply connected rank 1 symmetric spaces. And I will abbreviate this for as follows, because I will say it more than once. Okay. So this is an abbreviation for compact rank 1 symmetric spaces, this list of spaces. Okay. These are the classical known examples. And it turns out it's actually very hard to construct examples in general. There are other examples unknown, have been constructed. In the dimensions, I'll list the dimensions. So these, of course, occur in all dimensions. The spheres, these are in the even dimensions, etc. Okay? This guy really is exceptional in many ways. But so other examples are known in dimensions 6, 7, 12, 13, and 24. So to this day, there are no known examples of positive recurrent manifolds that are not one of these in dimensions higher than 24. Okay. Now, how many are there? How many are known? In this dimension, there are 2 known examples. In this dimension, there's 1, and in this dimension, there's 1. In these 2, there are huge families. Many interesting examples. Okay. So that's about the examples, and I won't tell you much more about them, not at this point. But the lack of examples has to do not only because they're expected not to be so many, it's kind of expected to be a small class, but there are very few constructions also. And the main construction actually is the following. You take a positive recurved space, or you take any kind of space, and you take a metric projection for something else. Like you get something that has curvature at least as big as what you had before. So the curvature, the law of curvature bound stays the same or goes up. Okay? That's the basis for essentially all constructions, but one, I would say. Right? So if you start with something that's non-negatively curved, right? So this is curved more than Euclidean space. It means that geodesics approach one another at least as fast as they do in Euclidean space. That's what curvature greater than equal 0 means. Then you know that such a quotient has curvature greater than equal to 0 also, right? And if you are clever enough or lucky enough or whatever it takes, you construct positive curvature. So that's how the example is constructed. Okay. So you need a source of manifolds with curvature greater than or equal to 0. And a very good source are Likus. Okay? But that's another story. So that's on the example side and the constructions. So, but what's ironic is that if you look at the obstructions that are known, then there are not so many, which is frustrating because not knowing many obstructions means that there's a lot of space there to look for examples, and there shouldn't be so much space. Right? So what are the obstructions? There are the classical ones. There's the Bonnet-Myers theorem. It simply says that, and maybe let me just throughout this talk say that I will throughout assume this. I will look at manifolds M where the sexual curvature is bounded below by 1. If it's some other bound, I'll just scale it back to 1. Okay? So, or tell you otherwise, whatever I mean. Okay? So if I don't say anything else, this is what I mean. But nevertheless, let me just add it in here again. And I'll just make this very short.
And they're all compact.
That's a very good question. So they're all complete, okay, as a metric spaces. You always deal with complete because otherwise you can do anything, okay? But if you have a positive recurved complete manifold and it is not bounded below, then it's, in other words, if it's non-compact, complete, positive recurved, it's actually diffeomorphic to Euclidean space. That's a very deep theorem, by Romal and Meyer. And the extension is the Chico-Romal-Scholl theorem. Okay? So when you have non-compact manifolds of non-negative curvature, they basically are bundles over compact ones. Okay? But if you have a lower bound and it's complete, it's automatically compact because of what I'm going to write down here. Okay? So if the sexual curvature, so I always assume complete in other words, right? So sexual curvature bounded below by 1, so it curves more than the unit sphere, then it's at most as big as the unit sphere. That's a classical theorem. It says the diameter of M is at most the diameter of the unit sphere, which is what? That one is pi. So the largest distance between any pair of points is pi. Okay? So it shrinks. Okay? So this in particular implies that the fundamental group is finite. Because if you take a manifold, you can go to its universal cover. It has the same curvature bound, so it has bounded diameter. So it's compact. And then you conclude that the fundamental group is finite. This is the classical result. Now, you could ask, are there some theorems about the structure of the fundamental group? Well, there are some, but only under additional assumptions, always, right? And so, in particular, to this day, any finite group is potentially the fundamental group of a positive curve manifold. This is probably not true, but still. There was an old conjecture by Chern, which is analogous to the situation in negative curvature. Curvature less than or equal to 0. Therefore, manifolds with curvature less than or equal to 0, you know, if you have an abelian subgroup, it's actually cyclic. Okay? Oh, sorry. Yes. Yes, if it's negative curvature, it's cyclic. If it's is cyclic, infinite cyclic, okay? So Chern proposed years ago, back in the late 50s, that the same thing is true in positive curvature. And at the time, one only knew the spheres and these spaces and a couple more, and it was true for those spaces, right? Well, it's false. Okay? It's not true. So there are examples with fundamental groups Z2 plus Z2, Z3 plus Z3, and that's about it. That's known. Okay, so this is one, certainly one obstruction. Now another one, you can say a little bit more if the dimension is even. Well, actually say a lot more if it's even. But look at the fundamental group of an even-dimensional manifold of positive curve. You know what it is, actually. Because this is either trivial or Z mod 2. So there you know completely what it is. Right? And the reason is, this is due to Singh. He's not pronounced Singh, as I always thought he would. He's Irish, and he's pronounced Singh. I have it from authorities. They tell me it's Singh. So,
as an Irishman, I confirm that.
You can confirm that.
Yes, I can confirm that.
So Singh, and this is one of my favorites, by the way. What he did was phenomenal there. So what he proved was that if the manifold is orientable, it is simply connected. Okay? Then, of course, if it's not orientable, the fundamental must be Z mod 2. You just go to the twofold orientable cover and it's simply connected. But his ideas have had a lot of impact on other things that I won't have time to talk about. But this is one of the tools, actually. So that's about the fundamental group. What else? Then there's Gromov's theorem, Betty number theorem, which says the following. It's actually much more general, so let me formulate it under this condition. And it's even more general than what I'm going to do here. But if you say non-negative curves are compact, dimension n, then so there exists a constant c depending on n, such that for any non-negative curve manifold has the following property. The sum of any numbers, or take homology with any field of coefficients, is bounded above by C of n, where n is the dimension of the manifold. Okay? So that's a really powerful obstruction to having non-negative curvature, right? So there's a bound on how big the Betty numbers can be, a universal bound. Depends on the dimension. Okay? There's a similar bound on the number of generators on the fundamental group, by the way. But and in particular, this is true if the curvature is positive, of course. Right? If the curvature has a lower bound that's negative, then the same thing is true, but then the bound also depends on the diameter. Okay? And now you can see. Of course, if you throw in the diameter, you can always scale the manifold if its curve is greater than 0, so the diameter doesn't matter, right, in this context. Okay. So this is Gromov's theory. Now, in addition to this, the only other known obstructions are obstructions to even positive scalar curvature, which is much weaker. Right? And that's not a general type of obstruction. That's for spin manifolds. Then you know that the so-called A-hat move genus will have to vanish and so on. Right? So the fact of the matter is that there are really very, very few known obstructions also. Right? There are conjectures. I mean, there's the classical conjectures of Hoff. I mean, one is about the Euler characteristic. The Euler characteristic ought to be positive, of a positive curve manifold. Not known. Then there's a conjecture that's attributed to Bott that says that the one formulation of it, I think this certainly would be Bott's formulation. If you look at the loop space of the manifold, then the sequence of Betty numbers grows and goes polynomially. I think that must be what we have in mind. That has very strong implications if it's true, right? It proves that the manifold is rationally elliptic, and then you can just deduce lots of properties. But it's not known. Okay, so what are the methods that have been used? So the methods to try to make some headway. Well, in a way, I think the methods goes back to thinking about the unit sphere in different ways. At least that's how I think about it now. So one is, so I'll call one of them, I'll just give names to them, shape, size, and symmetry. So what do I mean by this? Okay, so this, the first one, I'll just think about the curvature bounds, the so-called pinching of the curvature, right? So, so now I will violate, because this is what is normally done in the literature, I will normalize upper bound to be 1 for this discussion. Okay? Of course, you can always state it the other way, but if some of you are used to this is called delta pinch. Of course, it just means that the ratio of the minimal to the maximal sectional curvature is delta, right? That means equal to positive degree. Now, now then you could, why is this, what does this have to do with the unit sphere? Well, if the curvature is constant, and let's assume m is simply connected also. If the curvature, if delta is 1, then we're talking about having a constant sectional curvature, right? And then it's a sphere if it's simply connected, right? So then the idea is, what happens if I perturb it? Okay, so let's move delta a little bit. Say curvature almost constant. What can you say? And Rauch was the first to actually prove that in some neighborhood for delta close to 1, one can actually deduce that the manifold is a sphere. It's simply connected, homeomorphic to a sphere. So this became known as the sphere theorem, and today we know the following. If the sectional curvature is bounded like this, and let's say M is simply connected, then M is diffeomorphic to a compact rank 1 symmetric space. Okay? So the classical work was done by Rauch, Berger, Klingenberg, who obtained this with homeomorphism instead. Okay? Actually, the diffeomorphism part is interesting only in the, if it's not one of these spaces here. If that's not the topology. Already, if that's the topology, it's known that it's isometric to these spaces. It's a rigidity theory. Right? One knows diffeomorphism now, since the work of Brendel and Shane, which used the Ricci flow to actually produce a metric of constant curvature, unless it was one of these spaces. Okay. So now you can only go, you can actually go a little bit, you can take a quarter minus epsilon. And then you have an up to diffeomorphism. So here there's a rigidity theory, like I said, if you were not a sphere, topologically you're actually isometric to one of those model spaces, right? If you go below that, it's actually still true that you have a manifold which is diffeomorphic to one of those spaces. Now, and then after that, there's nothing known, right? Other than there are known examples with various pinchings, right? So the idea of trying to analyze this by letting delta become smaller and smaller and smaller and approach 0 sort of dries up quick, right? At least so far. They haven't gotten much out of it. Okay? So that's one approach, has beautiful theorems, but it ends kind of here. So far, anyway. Now let me move on to the size. So what do I mean by the size? Well, the starting point is actually the Bonnet-Myers theorem that I mentioned before. that illustrates already size, namely here, right? It says if I have curvature bounded below by 1, then the size in terms of the diameter is bounded about by that. Okay? So then the idea could be, and again, then there's a rigidity theorem that says if the diameter is equal to pi, then the manifold is isometric to the unit sphere. So that's another property of the unit sphere. So the unit sphere has constant curvature 1. It's also the largest manifold of curvature greater than equal 1. Right? In the sense that it's the only manifold with curvature greater than equal 1 with diameter pi. So it's an extreme example in that sense also, right? So therefore you want to relax that, right? So what happens if you relax the diameter? Okay? So you know that the diameter of M is at most pi, and actually you might assume it's less than pi because if it's equal to pi, it is the unit sphere. That makes sense, right? So then there's a theorem which is very much like this one that says that if you have sectional curvature of M greater than or equal 1 and diameter of M at least pi divided by 2, that's half of what it is maximally, right? Then you can conclude that M is either a sphere topologically, and this one is up to homeomorphism, or it is isometric to a list of spaces, and there are the crosses, or some quotient of the cross, even of the sphere. And I won't tell you the complete list, but it's completely known. Okay? So this actually is more general than this one, except for the statement of homeomorphism. It's because being quarter pinched actually implies this thing about the diameter. It implies much more than that. Okay? So this is more general, but this is the best that's known. So if you think about the diameter, it could be pi at most. Here we have pi over 2, and we know everything up until this point. Well, here's 0. We go below here, even the slightest bit below, we know nothing, right? There's nothing known. So that approach also dries up, right? So you want to understand them as the diameter becomes smaller and smaller, and see if something else comes up, and nothing has actually helped any further so far. There's a lot of geometry improving these things, but this kind of stops there. So what's the last one? Well, the last one is the following, where I also like to think about the sphere as an extreme object. So it's also extreme in the sense of the number of symmetries you have, isometries of the sphere. The group of isometries is huge in this space, right? As a matter of fact, it's the large, if you look at the group of isometries of an N-manifold, it has dimension at most the dimension of the isometry of the sphere. Or if it was Euclidean space or hyperbolic space. The constant curvature spaces, the simply connected constant curvature space, have the largest degree of symmetry in the sense that the isometry group that acts on it has the largest dimension possible. That just characterizes those spaces, right? And so in particular, the sphere is characterized by having a large isometry group, okay? So then the idea is, okay, so let's start from large, and let's relax the size of the group, okay? So now we don't say anything about the curvature, what range it's in. We just say positive. Might as well say greater than or equal 1. And then a big group that acts on it. And then small and small and small and small. Now what can you say? Okay? So that's the last approach. And the one I will discuss now. So the idea is, so the guiding principle is the following. Describe, maybe classify even, positively curved manifolds with large or special, with some recently, because this is fun too, special symmetry group. By symmetry group, I mean isometry group, right? So this actually has this sort of proposal to try to do that has a lot of potential in the sense that anyone can actually work on his or her own problem, right? By deciding what you mean by large, or what you mean by special, or what you mean by describe or classify, right? You can classify up to anything you want, right? Up to some kind of weird, maybe some Benny numbers are the same, or maybe they have the same homotopy type, or this and that. Lots of things are out there, okay? And this is what has happened. There's like a lot of things has come out of this, okay? So there's a lot of classification theorems or classification type theorems. I will mention only one. And now, before I do that, let me give some examples of large. Examples of what large could be. Like I said, it's up to you to decide, and if you come up with a notion, there's a problem to work on. Okay? So it could be what I just said, the dimension of the group that acts, right? So large could be dimension of the isometry group. M is large, of course, compared to the dimension of the manifold, right? This is certainly one way of being large, right? It could, something that's also turned out to be important is the rank of this group, the largest torus that can act, right? So it's a special type of group, right? Let me not mention that, but that's another. So this is always a Lie group, right? And so you can think about what's the largest rank of any Lie group that can act, right? Which means what's the largest torus that can act isometrically on the positive curve space, right? Turns out to be a very important question. Let me just leave this as one. So another one is, if you think about a group that acts on the space, you would say it's large if the orbit space is small, right? So for example, dimension m bar g, this is the orbit space, the space of g orbits. I guess I just switched all of a sudden. G is maybe inside the isometry group or the whole isometry group, okay? So then you also say the group G is large, right? One way to be large is if G acts, if this could be a point, right? If G acts transitively on the space, it's certainly large, right? It's not a symmetric space like I mentioned before, but it's a homogeneous space, okay? So then this would be just 0, right? And they have been classified, so that's an example, okay? Actually, long before this kind of idea was formulated, okay? So the positively curved homogeneous manifolds are known. And that list, I erased the numbers before, but it had actually, it had all these numbers in it also, right? 6, 7, 12, 13, and 24. The difference is, in terms of how many of them were, if you look at the homogeneous ones, there's 1 in all those dimensions, except 7 with their infinite. So, examples. So, okay. I mean, there are always these guys. Oh, oops, they used to be up here. So the contact rate 1 symmetric space. So you have to add the number of those each time to what I said. Okay. So this could be small. Right? You would say that's a reasonable thing to say. This number is called the cohomogeneity of the action. I used to hate this word because I couldn't say it. So Wu Yisheng came up with this terminology, but I'm getting pretty good at saying cohomogeneity. it's the dimension of the orbit space or the co-dimension of the principal orbits. That's what it is. Okay? So here's a theorem, a phenomenal theorem using Wilking. It's the following. So we assume M has section curvature positive, could be grade 1, simply connected. And let's say it has dimension N, okay? Now let's look at any fixed cohomogeneity, okay? So if we, so the theorem is the following. So you have a group that acts on it, symmetrically. So the dimension of the orbit space is K, right? Now, this implies the following, that if n, the dimension, is at least 18 plus 1 times 1 plus k squared. And this is assuming k is at least 1. If this is true, then M is like a compact rank once in the space. Okay? So what am I saying? I'm saying if you fix the cohomogeneity, K, you look at all manifolds of positive curves that have such a large group action, that the orbit space has dimension K, then if the manifold itself has sufficiently high dimension compared to that K, then it's like a standard space. Right? That's what the theorem says. So in particular, it mimics this thing about the finite list, about not these spaces showing up anymore, right? Like homogeneous ones, they die at dimension 24, right? And then you don't find any other homogeneous ones except the rank 1 symmetric spaces. This is true no matter what cohomogeneity you fix, right? You fix a cohomogeneity, then depending on that number, you go up in dimension sufficiently high, and above that dimension are the only, you don't find any other spaces. So the only new examples, so to speak, are in these finite linear dimensions, right? It's the same kind of phenomenon. So that's what it says. This is an example of what I said about type of classify. This is actually pretty good, but it's not diffeomorphism. It's not homeomorphism, but he did it up to tangential homotopy equivalence, which is already pretty good. It could be true up to diffeomorphism, but why not? But that's the theorem. Now, what does it say if k is equal to 1, right? So you notice that I was quick here today by saying k is at least 1, but that's because of the formula. Right? If k is 0, it's the same phenomenon, I just told you about it. But then this number isn't the right number, then 24 would be the right number. It's bigger than 24. If I say bigger than 24 would be the right number. Now, what is this number? In the simplest case you can imagine, or you think the simplest case you can imagine, when the cohomogeneity is 1. So you have a one-dimensional orbit space. That's being almost as large as you could imagine. Okay? Right next after being transitive, it's cohomogeneity 1. What is this number? It's 4 times this, it's 72. I have done this more than once, so I remember it's 72. I don't even do the computation, I just remember. I'm proud I can remember it. I think I could compute it too. But, so Wilking's theorem says, and in cohomogeneity 1, above dimension 22, you'll find only things that look like rank 1 symmetric spaces. Well, it turns out you can do a lot better. Okay? So what can you do?
Is that a very old theorem, Wilking?
No, it's from the, see now, I don't think anything is